Success in science often comes from a mixture of hard work, inspiration, careful interpretation, and it has to be said, serendipity. And even then it's possible to be right and wrong about a line of investigation. But often the solution to a problem proves to be the most elegant. Many leading scientists have experienced those moments when all the evidence falls into place and nature reveals itself. Professor Sir John Cornforth, known to all his friends and colleagues by the name Kappa, has spent more than 50 years working alongside his wife Rita in the field of chemistry. He's one of the UK's most senior scientists. He jointly won the Nobel Prize for Chemistry in 1975. But Kappa has been deaf since the age of 20, and now, in his 80th year, he's still working in research at the University of Sussex. Well, today in Reflections on Science, we will explore Sir John's career and focus on the scientific research story which led to his receiving the Nobel Prize. And to help in this exploration, we have with us today three A-level science students, Natalie Quinn, Amy Winterson and Simon Coffrey, and two of Sir John's university colleagues, Dr. Stephen Caddick and Professor Philip Parsons. As usual, the rule of this discussion is if we get lost in the science, we stop to find out more. But before we get deep into chemistry, Kappa, perhaps you could first tell us how you became interested in science. I mean, did anyone in particular encourage you at school, for instance? I believe you grew up in Australia.
There was no science in my family. And initially, I had an idea of going to the bar. If I hadn't begun to become deaf, I might be a retired judge by this time. But I had to find something where deafness would not matter so much. It is fatal to a barrister or a judge. And I had a very good teacher at the time at high school, Len Besser, who encouraged his students in chemistry and in doing their own experiments. And so that is how I got hooked.
Yeah. Now, your deafness, I mean, can you tell us a little more about that? Has it been a real hindrance in your career?
Tell them a little more about your deafness. Has it been a real hindrance in your career?
My type of deafness is a progressive kind due to overgrowth of bone inside the ear. Sometimes it stops after a while. In my case, it didn't. It proceeded to total deafness. Well, I could hear a bit when I started high school, but not very much when I started university. I never heard a word of lecture. And so that kind of handicap makes you concentrate very much on what has been written. And also, of course, what you can do with your own hands. I have always worked in the lab with my hands. I still do. As for the other handicaps, it inhibits communication with your colleagues. But one handicap that you discover later is if you become well known, your disability tends to become more important than your science. I don't like that.
Now, Rita worked alongside you in your laboratory. Now, where did you two meet?
I worked alongside you in the laboratory. Where did we meet?
Rita was a year senior to me at university, and this is where I met. As I said, I worked with my hands and did my own experiments, and so I was a fairly good glass blower at the time. And people got to know that I could mend their broken apparatus. A time came when Rita broke the neck off a Clausen flask. and her friends told her about me, and so she brought this thing along, and I mentioned it. And that was how we first met.
The start of a long career, a productive one.
Start of a long career.
What caused you both to come to the UK from Australia?
What caused us both to come to the UK?
We had both at that time qualified as MSc at Sydney University. And that at the time was the highest degree that you could get there. If you wanted to get a doctorate, you had to go abroad. And there were 2 scholarships awarded every year among all of the 6 Australian universities at that time, which gave you 2 years abroad at the university of your choice. It is rare for the 2 of them to be awarded to the same university, still less to the same department of the same university. But in that year, in 1939, we won the 2 of them, and so we travelled together to England. And we had both chosen the same university.
And here you are now. Yes, wonderful. Now, the title of the programme is How to Be Right and Wrong. So I think now I'd like you to tell your own story about how you can be right and wrong in scientific research.
Now tell your story of how you can be right and wrong.
Yes. Well, this story comes from 40 years ago. You can see a picture, if you like, of how we were at the time. Not like now. And we were working at that time at the National Institute for Medical Research. In particular, the problem on which we were working was the pathway by which cholesterol is built up in the animal body from acetic acid. There you have the structure of cholesterol. It takes 18 molecules of acetic acid to make 1 molecule of cholesterol. And the pathway goes through about 30 stages, depending on how you count. At that time, the starting point and the finishing point were known, but only 1 intermediate state was known. All the rest was mystery. But about that time, some chemists at the Merck laboratories in New Jersey were working on growth factors for various microorganisms, and they were working with a lactobacillus, one of the bugs that make yogurt from milk, for example. And this particular species needs to have acetic acid added to the medium if it is to grow. But some extracts of natural origin, which don't contain acetic acid, could substitute for acetate in the growth medium. And one of them was called distillers solubles, which is a byproduct of whiskey manufacture. So they took a large volume of distillers solubles and fractionated it down until finally they got about 120 milligrams of an acid, which they called a mevalonic acid. It is a fairly simple 6-carbon acid. And it was not very difficult to prepare synthetic specimens. And from the nature of the synthesis, you could put radioactive carbon-14 into one of the intermediates. So you had this molecule labeled in particular positions, and they would feed that labeled material to the lactobacillus to see what he did to it. But then somebody at the same institute had a very bright idea of feeding the radioactive mevalonate to a system that could synthesize cholesterol from acetate. And it proved to be amazingly efficient in making cholesterol. Well, we were all very excited by this news, and it certainly did help very much in the task of unraveling the pathway into cholesterol. We wanted at the time a good supply of the natural mevalonic acid. As I said, it is not very difficult to synthesize, but if you carry out the synthesis in the ordinary way, you obtain a mixture of two forms of the product. This is because mevalonic acid has what is called a stereogenic center, a carbon atom to which 4 different groups are attached. And so it can occur in 2 forms which are related to one another, as a right hand is related to a left hand. And the natural product consisted of one of these forms only. It is possible in principle to start from the synthetic mixture and carry out a process known as resolution, whereby they are separated into the 2 forms. But in this particular case, it was extremely difficult. It still is, as far as I know, even with subsequent advances. And getting hold of enough distillers solubles and doing this fractionation again so as to get a sizable quantity of mevalonic acid would have been impossibly costly in time and trouble. So we decided that we would devise a synthesis from a natural product that was abundantly available and did have a stereogenic center, so that we could modify the groups about that center in the direction of mevalonic acid. And by far the most promising starting point was a substance called linalool. You will see why this is promising. 2 of these groups attached to the stereogenic center are the same as in mevalonic acid. So that if we could modify one of these groups in one direction and the other one in the other direction as appropriate, then we would finish with mevalonic acid. And we thought we saw a way to do this. But there were 2 snags. First of all, linalool, although it occurs very commonly in nature, it occurs in essential oils like basil, lavender, bergamot, cinnamon, many others, and it's the basis of quite a number of perfumes. It does not always occur in the same stereochemical form, and most usually it is isolated as a mixture of the 2. there was the easiest way to find out which form you have is to shine a beam of plain polarized light through a solution of your stuff. Some specimens will rotate the plane of polarization to the right, and then you know you have what is called dextral in the lower, and some of them will rotate it to the left, and then you have a predominance of what is called the levo. There was only one source of linear lower which contained only one particular stereoisomer, and that was the levo-rotatory form. It came from whole leaf oil. The second snug was that it is all very well to write a formulae of this kind. That is a picture of the mirror image form that we showed before. But how do you know what is the exact stereochemical disposition of the groups about this center? And come to that, how do you know what the disposition is in methylonic acid itself? So we were very happy that we had recent information about both of those points. Now, in those days, there was only one chemical substance, the absolute configuration of which was known by measurement instead of by guessing. And that was tartaric acid. By a special X-ray technique, it is possible to determine, or it was possible then to determine, the absolute disposition of these two groups. So if you had only one of these substances, you had to relate this chemically to whatever other substance you were interested in. And you sometimes had to go through quite long chains of chemical transformation before you could notionally turn one substance into tartaric acid or tartaric acid into this substance. Now, for methylonic acid, the information came from a natural product called quinic acid. It occurs in a lot of leaves and bark, and it was done by Duilio Arrigoni, who was then a rising young scientist at the Federal Institute of Technology in Zurich. Quinic acid was one of those compounds that had already been correlated with tartaric acid, so that its structure was given by this. Duilio did some chemistry. He turned this acidic group to a methyl group, and by some clever manipulation of this hydroxylated portion, he turned this chain into a carboxymethyl group and this chain into a hydroxyethyl group. And so he had made methylonic acid that way, and he found that what he had arrived at was the unnatural form of methylonic acid. Not natural methylonic acid, but its mirror image. But getting the mirror image, of course, is just as good as getting the stuff itself from the standpoint of determining the absolute configuration. So that was for methylonic acid. The second piece of information also came from Zurich. And it was due to the work of Vlado Prelog. You see him there in his 90th year. His 90th birthday was last year. And among his many contributions to stereochemistry was a process for determining the absolute configuration of alcohols by correlation. It was known as Prelog's rule. The basis of that rule is that if you have an alcohol, never mind this part of the molecule, if you have an alcohol with three different groups attached to the carbon bearing the hydroxyl group. And we suppose here that these groups are of different sizes. L for large and M for medium and S for small. Now, you prepare from this alcohol the ester with what is called an alpha oxo acid. Because of the disposition of these three unequally sized groups, you find that when this is attacked by an organomagnesium reagent, the attack is preferentially from underneath and not from above. There are only two directions of attack, from on top and from below. In this particular case, Vlado chose an alcohol which had assured absolute configuration and a good difference in size between the three groups around the alcoholic carbonate. And so he could expect that there would be a considerable preference for attack at this center on the side that you see, rather than from the other side, which is somewhat more hindered. Vlado verified his rule with dozens of alcohols, the absolute configuration of which had been found by other means. And it held every time. Menthol is a particularly good case. It gives a good difference between the two directions of attack. But what you are doing in this attack is to create a new stereogenic center, which is tied to the stereochemistry of menthol, this alcohol, by the direction of attack. And he chose the groups here and the attacking magnesium species, so that after he had hydrolyzed up the menthol, having finished with it, he had a specimen which had the same carbon structure as linalool. And by some chemical transformations, he was able to convert it into the tetrahydroderivative of linalool. And then he measured the optical activity of that. And so what he concluded from this was that the levorotatory form of linalool was the one which would correspond to the absolute configuration of mevalonic acid if we could carry out our chemical synthesis and turn one to the other. We were very pleased about this. And so we bought a pound of linalool from a firm of perfumers. And Rita started work on the synthesis. I'll try to illustrate it with these cards. Here's linalool, as we saw it before, but I've put it bottom to top. And now, you see it has these two double bonds. The first thing to do was to apply one of the processes discovered by Herbie Brown, who won the Nobel Prize for Chemistry in 1979. Effectively, the result of his process is that you add the elements of water to each of these double bonds. And when you have done that, the double bonds are gone, and you have two hydroxyl groups instead. In a trial, counting the hydroxyl that is already there. Two of these groups you can tie up in an inert form by reaction with acetaldehyde. And that gives you a protected trial. So that then you can oxidize with a special preparation of chromic acid, so as to get the protected ketone. As a ketone, that is susceptible to what is called the Claisen reaction with methyl formate and sodium methoxide, so that you have introduced a hydroxymethylene group next to the ketone. All this rigmarole has the effect of weakening this chain to oxidation by sodium periodate, so that when you treat this with an aqueous solution of sodium periodate, this was a new process at the time, then bingo, methylonic acid. The protecting group comes off in the workup. And so all that went very well. We had our methylonic acid and we proceeded to measure its optical activity. And we found that we had got the wrong form. It wasn't the natural form, it was the unnatural. That meant that either the attribution of absolute configuration to methylonic acid or the attribution to linalool was wrong. But which? Now, in those days, when, as I said, you had to determine absolute configuration ultimately by correlation with tartaric acid. It was an extremely laborious process to find out the validity of a chain of connections like that. Nowadays, you can take your atlas of stereochemistry from the shelf and you can look up this particular thing and it will give you all that with references. Not then. It took me about a week of continuous work in the library to trace the chain backwards from quinic acid, which was what Duilio Arrigoni used to tie up with methylonic acid, right back to tartaric acid. But there was no joy there. Every link in the chain was solid. I never did have any doubt about the validity of Duilio's synthesis of methylonic acid from quinic acid, but I went over that too, only to be even more convinced. Then I thought that maybe there must be something wrong with the absolute configuration assigned to menthol, the compound that Vlado used. So another long search, and again no joy. Menthol was solid. So finally I took a very careful look at Vlado's paper, which he had done with a Japanese collaborator, and found that he had misapplied his own method. Mm-hmm. if you drew the correct conclusion from his experiments, it was that not lever rotator lateral, but dexter rotator was related to the natural form of mebylonic acid. The very last thing we had thought of when we started this work was having to tell a very distinguished chemist that he had misapplied his own method. In the end, we wrote to Vlado, pointing out our findings and offering our help in putting the matter right. It's a good index of the quality of a chemist by how he reacts to his own mistakes. And Vlado didn't disappoint us. He made no attempt to blame his collaborator. He pointed out observations that had come along since then, which ought to have warned him that there was something funny about Lindelof. He wrote the correction, and we published it in German in Liebig's Annalen der Chemie, the only paper we have published in collaboration. And Vlado was happy because although his paper was wrong, his rule was right. And since that time, we have been close friends. And when we jointly won the Nobel Prize in Chemistry in 1975, he did me the honor of asking me to give the speech returning thanks from both of us. We had corrected an error, but we still hadn't made natural mebylonic acid. But even there was a happy ending. We were on a visit to Australia, and in a lecture in Sydney, I spoke about this work. And after the lecture, a man got up and asked whether we would like to have some dexter rotator linalool. And sure enough, in about 2 weeks, we had half a gallon of the oil of a particular kind of tea tree, which a man at Taree in New South Wales had grown. From this tea tree, working in Canberra, Rita and I distilled the linalool. We applied our synthesis. It went beautifully, and pretty soon we had 20 grams of the natural mebylonic acid, which was about 200 times more than anybody had ever seen before. Going back to England next year, I called in at New Jersey and presented Dr. Carl Folkes, the director of the Merck Labs there, with 1 gram of the pure natural mebylonic acid, which was far more than he had ever seen before. And using it, Rita was able to make a discovery, which was of considerable synthesis, considerable use in some of our wider task, which was in determining the stereochemistry of cholesterol synthesis. That is the end of the story. It was not a major advance. It became part of the fabric of chemistry and biochemistry. It did help in elucidating some of the wider problems. the reagent which we used in one of these steps is still known as the Cornforth reagent. Many people have used it since then and still do. Our findings have been picked up and utilized by chemists all over the world. But the lessons I draw from this are slightly different. First of all, we found that cooperation was a good deal more constructive than competition, and it can be worldwide. Secondly, research can be enormously stimulating. It takes everything that you have learned and invariably some more things that you haven't. And lastly, nature is often speaking to you most clearly when she says, "No, that's wrong. Look again."
I wonder if we can look a little more closely at the mevalonic acid to cholesterol, or the cholesterol squalene situation. I mean, Phil and Steve, would you care to say anything about that?
Well, perhaps I could just ask Kappa a fairly naive question. Kappa, you said very early on in your talk that separating the isomers of mevalonic acid would be difficult. It seems as if that would have been the easiest thing to do, given all of the problems which there were with correlating the stereochemistry of linalool. So why is it so difficult to separate the optical isomers of mevalonic acid?
Well, at the time when we started our work, this separation had already been done. Carl Falk said at the time it was the most difficult piece of resolution he'd ever had to do, and he'd done quite a number. But the principle of this resolution goes right back to Louis Pasteur. You have your mixture by synthesis. And it is a mixture of equal parts of right-handed and left-handed material. You see my hands, they are mirror images of each other. And if I held my right hand up in front of a mirror, I would see a left hand in the mirror. But from the standpoint of chemical reactions that are not carried out in asymmetric media, these two are identical. The two specimens will have the same physical properties, the same boiling point, melting point, viscosity, solubility, the lot. They differ in their effect on polarized light, but you can't use that. But if you take this mixture and you react each component of it with an asymmetric component, which has only one configuration, like that. You have taken this asymmetric component and you have reacted it with your mixture represented by my hands. Well, if you look at that pair, you will see that they are not mirror images of one another. And twist this how you may, you can't make them into mirror images of one another. So that means that their shapes are different. Their properties are different. Their physical behavior is different. And so, for example, by recrystallization, as was done in this case, you can gradually separate them until you have separated these two different things. And then you knock off this assisting group, and you have the separated right-handed and left-handed forms. Nowadays, there are lots of tricks by which you can do better. For instance, you can make a chromatography column in which the solid filling consists entirely of asymmetric molecules, chiral molecules. You pass your mixture in solution down that column, and if you're lucky, you will find that one form is not so strongly absorbed on this chiral column as the other, so they separate into two bands as they go down the column. And you can separate off one and then separate off the other. And so you have done your resolution in that way. Nowadays also, there are some catalysts which are chiral, asymmetric in this way. And when they are creating a new stereogenic center, then in favorable cases they will produce much more of the right-handed form than the left-handed, or the other way about. And so you can actually construct your synthesis starting from materials that are not asymmetric, but by means of this asymmetric catalysis, you finish up with one form or the other. And there have been some syntheses of mevalonic acid that depend on reactions like that. But this was later, much later. At the time, we had to do what we can. The synthesis that Vlado used, known as asymmetric synthesis, used the menthol, which nowadays would be called a chiral auxiliary, in order to influence the stereochemistry of a reaction at another part of the molecule. And that too has been refined enormously. But there, if we had to do all this over again, we could do it much more neatly. At the time, we had to do what we could.
In the latter stages of the synthesis of cholesterol, we notice that squalene oxide cyclizes through a cascade.
You noticed that squalene oxide cyclizes through what we know as a cascade.
And on the screen,
yes. There are several lessons to be learned from that one. Let us have the cascade. Now, you see, that is one of the intermediates on the way to cholesterol. You will see that it still hasn't got any ring, except a little one here, an epoxide at one end. And that is the thread from which the ring structure is constructed in a single operation. The process starts at this end by addition of a proton and creation of a positive charge here. You notice these 4 double bonds artfully disposed in a particular relationship to one another. The electrons of those double bonds travel in much the same way as a zip fastener works from one end of the molecule to the other. Let's have the next one, please. So that by the time the process is finished, your positive charge has been transferred right to the top of the molecule and 4 rings have been formed. The electrons woof, 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 woof. All that happens in a single process. And what is more, there is a subsequent rearrangement which is even more complex and also occurs on the same enzyme. You put squalene epoxide in and you get a sterol out, lanosterol. Now, this process is now known as a cascade reaction. It is obvious why. And it's really the first example of the cascade reaction. But chemists have taken this up, and although they have not been able to imitate absolutely the process by which the sterols are formed, they can do it with other examples. Here is one from Phil Parsons. In this case, you also have an electron deficiency here, which in a single process is supplied from one double bond to another and to a third, so that in this way all these rings are constructed in a cascade. Cascade chemistry is now quite fashionable.
Sir John, I think we've got an animated sequence here which shows how the squalene molecule folds up to produce the cholesterol. What a beautiful sequence. Phil, you've got something to say.
In essence, we start with a very simple acyclic material, and in one step we can, as Professor Cornforth said, zip together a number of rings forming a highly complex ring system under virtually neutral conditions.
Could I just interrupt, Phil, because it's not quite acyclic, is it, Phil? There is a ring.
No, we have one aromatic ring, but this, of course, leads to 3 more rings plus the original aromatic ring.
But in that folding up, in that cascade, the squalene epoxide has to adopt a particular configuration in space, which is quite specific, isn't it?
It certainly does.
Because you can produce 256 possible configurations of cholesterol, but nature produces one. Because there are 8 asymmetric centres in there, so you get 2 to the power of 8 different possibilities, but nature produces the one.
But again, if you build the model of this, it becomes obvious how this will fold in one specific way to form, at the end of the day, a steroid nucleus. We can do the same reaction in the laboratory with a number of acyclic polyalkene systems using free radicals now in neutral conditions to form very, very highly complex materials.
If you make a model of the squalene epoxide and look along it, all those double bonds participating, it is as if you are looking down the barrel of a gun.
Natalie, Amy, Simon, I'm sorry, Sir John has cornered the market in the conversation, but that's the reason he's here. Are there any questions that you have for him?
I was wondering, with this cascade, How do you ensure that the positive charge, the proton, is attached to the specific place in the molecule?
Cascade. How do you ensure that the proton is attached to the specific carbon?
The way the enzyme does it is by accepting the whole molecule of squalene epoxide at its active site, so that the epoxide is folded in its correct configuration, and there is an acidic group on the enzyme in exactly the right position. And there isn't an acidic group at the other end.
These are all enzymatic processes, aren't they?
But it's important to know that you can do the same thing in a test tube,
Yes.
because there's a differential affinity for a proton between a double bond and the oxygen of an epoxide. So in fact, so there's a lovely example here of chemoselectivity. That is chemistry is exquisitely selective, so that even a proton, which is quite a reactive species, looks around the molecule and then reacts with the most reactive species.
And very often, of course, you can use a metal to initiate this.
Yeah.
A metal that will bind specifically to oxygen. A metal like tin or titanium, which has a very, very strong affinity for oxygen and not a double bond. So you could bind, for instance, titanium tetrachloride to the epoxide and induce exactly the same cyclization.
Amy?
Why is it that the two isomers of methylonic acid are called R and S? And which is which?
Why are the two isomers of methylonic acid called R and S? And which is which?
This is a convention in which, by the way, Vladimir Prelog took a part in framing. The other two people who constructed this convention were Christopher Ingold, a very famous physical chemist of this country, and R.S. Kahn, who was the editor of the Journal of the Chemical Society at the time. So it is called the Kahn-Ingold Prelog, or CIP system. At the time, they were faced with the fact that absolute configurations were being determined thanks to the elucidation of the tartaric acid molecule. So they wanted an unambiguous way of describing the stereochemistry about the stereogenic center. Now, let's see, what I have here is R. And the reason for this is the four groups around the center are ranked in order. First of all, the first rule is higher atomic number precedes lower. So that the oxygen here, which is the highest, is obviously 1. And for the deduction of the other, you have to proceed a step further away from the center. Here, you have two CH2 groups, but one of them is attached to hydroxide. And the other one is attached to a carbon. And in the third one, the methyl group is attached to a hydrogen. Well, proceeding to the next order of differentiation, this is obviously the lowest rank. So that's number 4. And in distinguishing between these two, oxygen takes precedence over carbon. And so this is 2 and this is 3. Now, you are holding the steering wheel of a car. The shaft of the steering wheel is going towards your lowest strength group, in this case the methyl. The 1, 2, and 3 rank groups go around clockwise like that. In other words, you have to turn the wheel to the right in order to go from 1 to 2 to 3. That's how you remember the convention. And similarly, R, that is R, it stands for rectus. If you turn it the other way, you turn it to the left, you have a sinister. And that's not what it seems. Sinister just means left in Latin. So you have that convention. It is purely artificial, but it does serve to designate unambiguously the structure that you have. You haven't learned that? No, you will.
It will come. It will come. Sir John, I know that you've got a wicked sense of humour, and I'm sorry that we're running out of time. It only remains for me to thank our discussants, that's Stephen and Philip, and of course Natalie, Amy and Simon, and of course thank you very much Sir John and Lady Cornforth for sharing some of the highlights of your career with us. Thank you very much.